Hello, everyone. Welcome to pre-lecture 4. This is going to be before our class for Thursday, January 20th. So to jump right in, last class we talked a little bit about phase transitions and this pre-lecture, and then in class on Thursday we're going to talk more about quantifying the energy related to those phase transitions. And so one of the ways that we can measure that is using this equation, which hopefully looks familiar from General Chemistry 1, where Q is the heat of a system is equal to the mass of that system, the mass of the substance. C is a specific heat, which is going to be a constant for whatever substance we're measuring, and then a change in temperature. And so essentially, if you're having a change in temperature, that means you are not undergoing a phase change. And that means that you can quantify the heat by measuring, again, the mass, specific heat, and the change in temperature. Okay. It doesn't matter which way you're going when you are doing this. So you can have a negative change in temperature. If you're cooling something, for example, then it would have a negative change in temperature, as long as, again, you're not undergoing a change of state. And so consider an example. If we have a pot of water boiling, then if we have it on our stove burner, then our burner will supply heat at a roughly constant rate. And initially, that heat will serve to increase the water's temperature, where we have, again, the ability to quantify that with Q equals, I tend to abbreviate this MCAT, so Q equals MCAT. And then when the water reaches its boiling point, the temperature will remain the same. We know that water at about sea level boils at 100 degrees Celsius. So once we reach 100 degrees Celsius, the water will continue boiling, but then our temperature will remain constant as that heat is now being used to transform water from being a liquid to being a gas as it is boiling. In that case, we can quantify heat in a different way using this Q equals N delta HVAP. And so what that means, Q still is heat. N is going to be the number of moles of our substance. And then delta HVAP is a constant that we can measure that is our heat of enthalpy that we discussed, heat of vaporization or enthalpy of vaporization that we touched upon last class. Okay. If we're to graph this, we can measure the amount of heat added. We could also measure this as time. And then our y-axis would be temperature. And so anything shown here in blue is representative of a phase change, where we would use Q equals N delta HVAP, or if we're going between a solid and a liquid, we would use Q equals N delta H fusion. So this is our enthalpy of fusion, right? Otherwise, for all three of our red lines where we have changes in temperatures, we can use Q equals MCAT. Something that is different is going to be C. So the specific heat for solid water, the specific heat for liquid water, and the specific heat for gaseous water are all going to be different. So we'll end up with different values for all of those. Otherwise, we can use the same equation each time. And so if and when you are to encounter a problem like this on a quiz or during class, for example, this is number 11 from our in-class worksheet. I ask you how much heat is required to raise the temperature of 39.5 grams of water from negative 45 degrees Celsius to 155 degrees Celsius. And I give you all of these solids. These C's are specific heats. And then I also give you enthalpy of fusion and enthalpy of vaporization. So how would we go about solving this? We would start at the coldest, basically. So we could realize that the first thing we need to do is heat the ice from negative 45 degrees Celsius to 0 degrees Celsius, because that is where our phase transition will start to take place. Then we do our phase transition, which is the melting of the ice. Then once all the ice is melted, we'll have liquid water. We can heat that water from 0 degrees Celsius to 100 degrees Celsius. Then at that point, we have another phase transition where we then boil the water. And then once all the water is no longer liquid, but a gas, we would heat that steam from 100 degrees Celsius to 55 degrees Celsius. And so if we start to quantify this, step one, again, we're heating the ice. If we have a change in temperature, we know we use Q equals MCAT. we'd plug in the mass in grams, use our specific heat of fusion, right? Specific heat of the solid, so our 2.09 joules per gram degrees Celsius, and then the change in temperature is positive 45 degrees, right? And so overall, excuse me, overall we end up with 3,380 joules. We can also then do the next step. So step 2, we would melt the ice, where we go, we have Q equals our number of moles. So we would take that 35.9 grams, use the molecular weight of water there to convert it to a number of moles, and then multiply it by our enthalpy of fusion, which is at 6.01 kilojoules per mole. And we would end up with 11.9 kilojoules. Something that I will point out here, or two main things, is that anytime we're changing temperature, we're going to be in grams. Anytime we're changing phase, we're going to be in moles. So that's something to keep in mind. You can always follow the units on your constant. So you'll notice that grams shows up in specific heat, moles shows up in enthalpy of fusion. And the other thing is that our answers are going to be different units. And so our specific heat constant is in joules, our enthalpy is in kilojoules. And so it doesn't matter if you report your final answer in joules or kilojoules, but you just need to be consistent throughout. Okay. All right. So we'll keep working on that problem in class. If you want to try and finish it yourself, you can go ahead, but we will dedicate some time to working on this in class. Great. Our next topic is going to be phase diagrams. And so if we measure all of our substances boiling and condensation points, melting, freezing points, if we make those measurements across a range of pressures, we end up with something called a phase diagram. And so the idea of a phase diagram is it will plot the pressure of something versus the temperature of something, and it will measure the boundaries between all of our phase transitions. And so why are these diagrams useful? They indicate that the physical states exist under specific conditions of pressure and temperature. Essentially, if we change one or both, we could end up with a phase transition. We'll also provide pressure dependence, phase transition for temperature, for anything we may undergo. And so what does this actually look like? Again, we graph pressure versus temperature. And then we have these lines. And anytime you see a line on a phase diagram, that represents a phase change. So if we're going from a liquid to a gas, for example, we know it's vaporization. If we're going from a gas to a solid, we know it's deposition. And so anytime we cross those lines, that represents phase change. We also have two other points on here that I'll talk about on the next slide, a triple point and a critical point. So again, any line represents phase transition. Our triple point on that graph is where all three lines intersect. And all three phases are going to be in dynamic equilibrium at this point. And so this is a chemical called cyclohexane. This is actually what a triple point looks like. So you'll notice that essentially we have something that is simultaneously boiling, freezing, like it starts freezing as it's boiling. It is also subliming, depositing, basically doing all of the phase transitions at once. This is what having a triple point looks like, which I think is pretty cool. We also can think of something like CO2, and I could ask you, for example, like start at a certain pressure and change the temperature. Do we experience a phase transition? That could be another thing. With the other, so this would be our triple point. We also have a point called a critical point. And so that would, on this CO2 phase diagram, that would end up about right there. And the critical point is the point at which a liquid and gas no longer have distinguishable properties. And so we end up with something called a supercritical fluid. This will always take place at higher temperatures and higher pressures. And essentially what it means is we are not a gas, we are not a liquid, we're something in between them. Okay, and it will never turn into a liquid, no matter how much pressure is applied after that certain temperature. But it will also never be a gas, no matter how much the pressure is lowered. And so, or I guess it will once the pressure is lowered below that, but essentially we have a cutout there where we will no longer reach gas or liquid So this is something that I talked about last class, using supercritical CO2 for decaffeination of coffee and tea. If you'd like to learn more about it, you can check out this link for a demonstration of it. Anyway, that'll be the end of our pre-lecture. If you have any questions, please let me know. Otherwise, I'll see you in class.